morning, good afternoon, everyone. Welcome to this first session of the theme 5, how can science better inform public policy, governance and capacity building for water, food and health. My name is Aurélien Dumont. I'm from the Groundwater section of the Division of Water Sciences in UNESCO, and I will chair the session on behalf of Alice Aurélie, who is the Chief of Section of Groundwater and Settlements, the Division of Water Sciences, who is member of the scientific committee, but unable to join this morning.
Thank you, Aurélien, and good morning, everyone, or good afternoon.
And just a few additional words before starting. As you will listen, this theme will be showing real example of how scientific knowledge is taken by decision makers or give insight to the policy choice that have to be made. We will have also the presentation looking at some educational aspects, especially in the second part of this theme tomorrow. And as a whole, this theme on the role of science for policy and capacity building is very in line with the objective of the 8th phase of the International Hydrological Program of UNESCO, that is in fact ending this year, and the 9th phase will start in 2022. And this is why this was important for UNESCO Division of Water Sciences to be involved in and support this theme. This is also noticeable that many presentations analyze the role of groundwater resources, especially in this theme, but also in other presentations during the conference, as you may have noticed. And I was saying it is important because the groundwater-based solution in terms of storing water, maintaining dependent ecosystem, especially during low flow seasons, for instance, definitely need more consideration, and definitely from the UNESCO side, this is something that we welcome that so many speakers highlight the topic of groundwater. Well, we will start now, but before giving the floor to our first panelist, I would like to mention that the keynote of this theme 5, will be given tomorrow at the beginning of the second session. This will be by Mr. John Edgens of the WEB project, who will tackle his approach on promoting water education, working at multiple levels and with different audience. So I invite you to connect again tomorrow to hear this keynote on this very promising, interesting topic. So now I will give the floor to our first presenter. So I understand they will little bit modification from the online program. So the first panelist today will be the Dinah Mudimbu from the Department of Chemistry and Earth Sciences of the University of Zimbabwe. So please, Dinah, the floor is yours.
Thank you. Good morning. So this morning I'm here representing a project called Census. It's also a network. And in Census, we are looking for this morning on the capacity building in multidisciplinary scientific methods for improved understanding of the impact of conservation agriculture on groundwater resources in Africa. As a background, we are saying there's up to 70% of the populations in sub-Saharan Africa relying on groundwater resources, and the development of groundwater systems is instrumental in food security and access to safe water. And when we look at what's being reported by SADC countries, there's been an experience of higher and higher land and ocean surface temperatures as a result of global warming. And this is leading to extreme conditions. And the 2015-2016 drought that left at least 27 million people in the SADC region that were left food insecure as a result of poor harvest. So when we look at this coping mechanisms that the countries in the SADC region have come up with, these include introduction of climate smart agricultural techniques, such as conservation agriculture. And in conservation agriculture, this is looking at the implementation of key principles of minimum soil disturbance or zero tillage, use of crop or surface residues, and crop diversification or rotation. And in all this is to improve the resilience of crops to certain conditions such as drought. In Zimbabwe, as an example, I'm from Harare, Zimbabwe. We have had in the past season, 2020-2021, at least up to 1.8 million smallholder farmers were targeted for training. And this was supported by FAO and a foundation called Foundations for Farming, in which farmers were trained in principles of conservation agriculture. And that was, it's been referred to as Pfumvudza. And this again is to help bring food self-sufficiency to Zimbabwe, working on a small plot and sufficient to produce enough to feed a family of at least 6. However, this begs the question, and one of the key questions that we're looking at as CIFAS is what is the impact of climate smart agricultural techniques, such as CA, on soil water dynamics, on agricultural resilience, and in particular, as I'm a geologist, on groundwater recharge. And in answering this question, one of the limiting factors that was identified is there enough research capacity in the relevant physical sciences to be able to answer this and other questions involved with conservation agriculture? CIFAS stands for Strengthening Capacity in Environmental Physics, Hydrogeology, and Statistics for Conservation Agricultural Research. And it's a joint undertaking between colleagues from Zambia, Zimbabwe, Malawi, and the United Kingdom to strengthen our shared capacity amongst the statisticians, the soil scientists, geophysicists, hydrogeologists, agriculturalists, and social scientists. And this is in looking at those issues of conservation agriculture and on a holistic level, what is the impact then with respect to soil water fluxes and groundwater resources? And the processes that we're looking at in terms of what we're doing within CIFAS, we're looking at what is the available water for crop growth then. And this project started in 2017, just to go back a bit. And we've looked at processes of how much water is available for crop growth when we are looking at the use of conservation agricultural techniques. And when we look at the soil profile, what is the profile water recharge? And is this addressing the resilience issue in terms of how much soil water is available for the next season, if any, in terms of when we use conservation agriculture in comparison to other agricultural systems, such as conventional systems? And then further down in groundwater recharge, which is a key resource, can this be sustained then by the different agricultural method that is used on the surface? And investigating these processes, we've employed a number of measuring and modeling techniques, and looking at soil water properties in the field, tests and lab measurements. We're examining the connection between water at the surface and deeper in the profile using shallow geophysics. We're looking at direct methods of monitoring water levels, as well as chemical methods, use of isotopes, CFCs, looking at measurements of residence time, estimating recharge, and trying to get a sense of how much groundwater is, how much the groundwater is changing under the different agricultural systems, such as conservation agriculture. And then we're integrating all these measurement results that we're getting from the different measurement techniques. And as the different scientists and different disciplines, we look at different components of what we've measured and integrating to see what are the results telling us, coming up with statistical processes and innovative ideas to bring out the relationships that may exist and allow modeling, prediction, and upscaling to national and regional levels. On the socioeconomic assessments, which is also part of this project, we're looking at integrating to enable addressing issues of involvement of farmers, policymakers, and relevant stakeholders, and how outcomes of the scientific research can benefit the different players. From the hydrogeology working group, we've had a chance to link observations in the soil in the top 1 meter of the groundwater, looking at monitoring boreholes that have been drilled within the fields, and all these monitoring boreholes have been instrumented with automatic loggers to be able to monitor changes in groundwater levels. We've had these fields instrumented with electrical resistivity tomography to visualize and measure water movement in the subsurface, and bringing groups of scientists that don't usually work together out of our comfort zones and strengthening capacity to enable the different groups to initially understand what the other discipline does, and then have a fresh look at the issues of conservation agriculture and come up with innovative approaches to integrate our data. On a capacity building level, we've had training workshops, and in these training workshops, we've been able to look at physical-chemical parameters, and this is reinforcing standard practices and procedures within, particularly when we look at the groundwater working group, looking at physical-chemical parameters and their measurement, how we are doing our groundwater sampling, collection, and measuring various elements and isotopes that we will use in the groundwater recharge estimation. We've looked at pumping tests to gather information on hydraulic properties and standard procedures for that. Looked at ERT instrumentation and in the shadow geophysics, how we can use that within our groundwater component and share that with the bigger multidisciplinary group, and in the integration of the techniques in analyzing our data. We've had a number of key lessons come out of this, bringing together or grouping of people from different disciplines. And in this, we've been able to have an opportunity to work together and building equitable partnerships. And this was possible because the different partners in the different countries were able to be on the project from project conception. And this has promoted the realization of genuinely equitable partnerships. In training, it hasn't only been focusing on academic skills, but also within the 3 countries, it's been looking at on-the-job training for different career scientists, from very experienced working with students, working with interns, working with lab technicians. So it's brought together different groupings of people from different levels. The value is being realized through a number of approaches as well, of training the trainer, because the institutions involved, our university institutions, will be able to pass on skills to our students. Early career research scientists are able to participate in the work group leadership and outward-facing project activities as well. This work through Cephas has allowed a cross-pollination of ideas and generation of innovative methods and solutions, and scientists from different disciplines are asking new questions, and solutions generated are innovative and can better inform policies. The Cephas International Network is lending itself not only to the current project, but also future collaborations of national and regional significance. And for us, this is how we're using science to better inform public policy, governance, and capacity building for water, food, and health, and in particular, this issue of conservation agriculture and its adoption within the region, and how we can support or inform policies relating to that and groundwater fluxes. Thank you.
Thank you very much, Diana, for this very interesting presentation, and especially this link that you showed at the end of the presentation on how you see the role of science in the decision-making and policy process. And I don't think we have a question from the audience. Pedi, do you have any question or anything to add?
There's no question yet, so maybe we can move on to the next one so that we do everything at the end. Yeah. Okay.
From my side, I had just a quick question, clarification question on the, if you could just expand a little bit on what are the challenges to be solved. Do we have already an intensive groundwater use and a problem of balance between withdrawals and recharge, for instance, or the general objective of your research was more to characterize the natural flows and how to potentiate the recharge, so that I don't know, maybe yes, natural flow dependent ecosystems still have enough groundwater flow, and so you are able to have a more resilient environment as a whole. You know, this difference between, yes, already a sustainability challenge regarding the use of groundwater resources, or it's more like an initial assessment.
Yes, there's definitely a couple of issues in there, in that when we look at the research work or studies that have gone on conservation agriculture, there tends to be a generalization of what happens with respect to soil water and its potential to recharge the groundwater. And when we change the agricultural practices, then from conventional to conservation agriculture, are expecting that there is more water moving into the groundwater. There is that generalization in literature that, yes, there is potential, but we haven't measured it. So we found a gap in that from a hydrogeology perspective. We want to be able to inform policy correctly to say, as we change agricultural systems, what is the impact on groundwater? Because we rely so much on it. If 70% of our countries are relying on this groundwater for other use, one of the measures being taken by the SADC countries is to try and increase productivity in terms of food security by using irrigation. So again, we'll move into using groundwater, this resource. And if we're going to be changing the usage, then the change in practice is very important for us to know what's happening with those water fluxes.
Very, very interesting as an approach. So we can expand more in the final Q&A session. Thank you again. So now I will give the floor to the next speaker, who is Disha Gupta from the Delhi School of Economics. And again, this will be a presentation concerning groundwater. Please, Disha, the floor is yours.
Yeah, thank you so much for introducing me. I am a PhD student at the Delhi School of Economics, and I would be presenting a part of my PhD thesis today. Your questions and suggestions are more than welcome because that will help me improve the quality of my paper. India is the world's largest user of groundwater for irrigation, and there has been an increasing reliance on electric operated tube wells for extraction of water. In most of the regions in India, electricity is being subsidized so that farmers are paying some fixed amount, which I call here the flat rate fee, which is based only on the horsepower rating of the pump, which is not dependent upon their actual usage. And thus, they do not have the incentive to use these resources efficiently because, they don't reflect the true cost of provision of electricity, and thus they end up overusing of these resources. So in this paper, I would be looking at the case of Punjab, which is a key agricultural state in India. It is important in studying the groundwater situation in the state of Punjab because it has the highest groundwater utilization with respect to recharge if you compare it to any other region in the country. So prior to 1997, farmers were charged a flat rate fee of rupees 50 per horsepower per month. But in February 1997, a policy of free farm electricity came in. So in this paper, I would be looking at the impact of this policy change. In particular, I'm interested in looking at the impact of lowering fixed electricity charges for tube well use from flat rate to zero on the number and type of wells installed and on groundwater depth. I would also discuss some implications for groundwater overuse. The figure that you see over here, the maroon shaded region, is the one that is Punjab. There could be various channels through which the free pricing policy could alter the behavior of the farmers. So post this policy change, electric pumps became cheaper because farmers did not have to pay any extra charge for using of these electric pumps. And due to the lower operational costs, farmers had an incentive to invest in electric pumps. Moreover, the fixed fee, which was earlier tied to the horsepower rating of the pump, now no fee needs to be paid. So farmers have a greater incentive to invest in pumps of higher horsepower rating. Before I get into the third channel, let me just briefly tell you about the two kinds of irrigation pumps that farmers usually use. First is the submersibles and second is the centrifugals. The submersible pumps are functional at greater depths and have a higher discharge capacity as compared to centrifugal pumps, which are functional at only shallower depths of about 10 meters. So in the third channel, I would be looking at the heterogeneous impact of this policy on groundwater depth for farmers that lie closer to the cutoff of about 10 meters, where a technological shift from centrifugal to submersible is required in order to have access to groundwater. And since they would switch to submersible pumps have greater discharge capacity, so we would expect that the impact on groundwater depth would be larger as compared to the full sample. I would rely on two sources of data. The first is a minor irrigation census. It is a village level data set. The variables that I get from here are the average groundwater levels, the number of dug wells, shallow tube wells, and deep tube wells. And I know each of these type of wells according to the water lifting device, according to the horsepower rating, and according to status. The second data source that I would be using is the Central Groundwater Board data. It is an observation well level data set. I have groundwater level of the test wells that is recorded for 4 times in a year. The impact of the policy change is examined using the differences in differences methodology, wherein the villages and wells in Punjab are taken as a treatment group, and those in the neighboring state Haryana, where farmers continue to pay a non-zero flat rate fee, are taken as a control group. A key assumption for identification of the DID model is that of parallel trends. I'm not going into details of this in the interest of time, but you could take a look at it in the paper. The model that I'm going to see over here is the standard DID model, where YIJST represents the various outcome variables I is the village or the well, J is the district, S is year, S is the state, and T is the year. D district are the district level dummies. D post is another dummy which takes a value 1 for the post-treatment period and 0 for the pre-treatment period. In the case of minor irrigation census data, I have taken 1993-94 is the pre-period and 2000-2001 is the post-period. For the Central Groundwater Board data, I have taken 95 to 97 as a pre-period and 2002 to 2005 as the post-period. Over here, D Punjab represents another dummy variable, which takes a value 1 for all the entities in Punjab and 0 for that in Haryana. The coefficient of the interaction term beta gives us the impact of the policy change. Epsilon IJST is the random error term. I also account for the possibility of spatial correlation using the approach proposed by Conley. I have taken a distance cutoff of 25 kilometers in the results that I'm just going to show you, but there are various cutoffs that I had tried. The details are given in the paper. These are the various outcome variables that I'm going to look at, mainly the number of wells, the number and proportion of electric operated wells, the horsepower load, and there are 2 variables relating to groundwater depths. So in the left panel, what you see, so these are the 2 figures from the minor irrigation census data. The left panel shows you the average number of dug wells and shallow tube wells in both the states in the pre and the post-treatment period. You would notice that there is an increase in the average number of dug wells and shallow tube wells in Punjab, while there is a decline in that of Haryana. One of the reasons for decline is well failures pertaining to deeper groundwater depths in Haryana that you can see in the figure in the right panel, which shows you the average groundwater depths in the 2 states, how they have changed over time. As you would see, the percentage increase in groundwater depth in Punjab is about 45%, which is much higher than that in Haryana at 39%. So you see that there is more depletion happening in Punjab post the policy change. That's just the descriptives that's showing you. This is a figure from the Central Groundwater Board data. The left one shows you the spread of the observation wells. For representation purposes, I've plotted wells from year 2002. Each dot shows you 1 test well. It just shows you that these wells are not concentrated in any one part of the state, but they are evenly spread out. The right panel again shows you the average groundwater depth of these test wells from the Central Groundwater Board data. As you can see that there is an increase in the average groundwater depths in both the states, but again, the percentage increase in Punjab is 31%, which is much higher than 25% in Haryana. Note that the average groundwater depths in the 2 states don't look very similar. The reason being that the composition of different types of wells are very different across the 2 data sets. Also, in this data set, we are talking about the test wells, which are not the actual irrigation wells. It is very important to remember this. And in the minor irrigation census data, those are the actual irrigation wells from which farmers are extracting water for irrigation. So coming down to the results from the minor irrigation census data, you would see that there is an increase in the average number of shallow tube wells and dug wells by 40. And the relative baseline figures are 76 wells in Punjab and 92 wells in Haryana. So there's a differential increase of the number of shallow tube wells and dug wells. And not only, so much of this increase is coming from the electric operated shallow tube wells and dug wells that you can see. There is a differential increase of 42 number of electric shallow tube wells and dug wells in Punjab as compared to Haryana. Not only have the numbers gone up, but the proportion of electric operated shallow tube wells and dug wells have also gone up. If you look at the horsepower load has increased in Punjab by 217 more as compared to Haryana. So, you know, these 2 channels of electric operated wells and horsepower shows you that there has been an increased groundwater extraction in Punjab. If you look at the percentage deviation in the groundwater depletion, this has also increased by 16% more in Punjab as compared to Haryana. Now let's look at the results from the Central Groundwater Board. The results are qualitatively similar. If you look at the full sample, there is an increase of 14% more of percentage deviation in the pre-monsoon groundwater depths in Punjab as compared to Haryana. But if you restrict the sample to looking at the farmers that are closer to the 10-meter cutoff, where there is urgent to switch to submersible pumps in order to have access to groundwater irrigation, the impact is even deeper at 21%. These are the results when I take pre-monsoon groundwater level as the dependent variable. The results that you will see are qualitatively similar. So for the full sample, the groundwater depths go up by 0.86 meters in Punjab. When you restrict the sample, the impact on groundwater depths become even sharper. So I'll just conclude my presentation over here. Free agricultural pricing policy has implications for groundwater depletion. I have shown you that in Punjab, there has been an increase in the average groundwater depths through the channels of increased investment in electric operated tube wells and pumps of higher horsepower rating after this policy change. And I also show you that this impact is even sharper around the cutoff of 10 meters, where farmers would be switching to submersible pumps in order to have access to groundwater. The findings of the paper has important policy implications. It highlights the need for agricultural reforms in the form of alternative pricing policy or incentives given to the farmers in order to promote efficient utilization of water and energy resources. Thank you.
Thank you very much, Disha, for this very interesting presentation, and sorry for the little technical problem of displaying, but you were very reactive and we could see the result of your research. So let's see if there is any. Again, I was just checking if there is any question from the audience. I don't think so, and I will invite our audience to still provide any comments or suggestions for the final Q&A session. Just maybe a question from my side to you. As you highlighted in your final words that some reforms would be necessary, how the users, the groundwater users, are seeing the situation regarding the necessity to undertake these reforms, and at the end, that if it's a reform that decided at the political level, the possibilities that they are really applied on the ground.
Yeah, so there's another paper of mine where I talk about the alternative pricing policy framework. So what I show over there is that if you implement a policy of, let's say, charging farmers that is closer to the true cost of provision of electricity, I saw that we would be saving a lot of water resources and without having a negative impact on yields. And this could be, there could be a conjunctive policy of having cash transfer for the farmers. So there needs to be a change in the policy design. So that's merely because of the policy design that we have, that the electricity is absolutely free, that farmers are overusing and they are cultivating a water intensive crop, paddy, which is a predominant crop in the state.
Perfect. Very, very, very interesting and very complex issue also, this relation between, of course, groundwater user policies and all the incentives to direct and the use and conserve all our objective environmental, social, revenue, and so on. So maybe we will have more opportunity in the Q&A session to discuss this aspect and on the role of science to enlighten all these issues. But for now, I will invite our next panelist, who is Mr. Sergei Myakov.
Thank you for keeping our time. I'm presented place of my country, Uzbekistan, on the globe place, and map of Uzbekistan around Kazakhstan, Turkmenistan, Kyrgyzstan. It is Stan. I must be explain this word. It's like Netherlands, England, and land in English and stand in Asia. And in rural areas, people use surface water to irrigated food and very often for drinking. Its main is to use water, groundwater and surface water have a similar hydrochemical regime. And we use GIS technology for showing us distributed the water surface quality and hydrological regime and some disease in the rural population. Hydrometeorological composition of ground and surface water of specific territories of the river catchment is usually the same. It is GIS map show distributed the incidence of rural population on administrative region in the Tashkent region. and water chemical regime. And histogram show total mineralization in the surface water. You can see in the upper part, it is small histogram, and lower part in the river. And different map of the incidents and the different color. Dark color, it is much more incident, and light, it's minimal. On this map, for show like one paradox. In the upper part of the river, where people use fresh air and fresh water without air pollution and water pollution, but in this region much more incidents and as in the middle part of the river. It is some paradox, because upper part, it is mountain region, and people use this territory as recreation. But for recreation, people use a short time for recreation, and short time use fresh air and fresh water. But rural people living in this region every day and many years, but it is unusual. They have much more incidence as in the middle part of the river. It is two maps. It is was unusual when medical people. I'm hydrologist, and we work for this project with Ministry of Health, and they for them was very unusual. Why they have question why people who use fresh water but have much more incidence on the middle part of the river. And this map example, we can compare the primary morbidity polygons, background color, and the mobility values of the CS of the gastrointestinal tract. It's density of dots. And this slide show us example. We can compare two types of different illness. And for analysis of the risk of assessment of the evaluation of the illness in the rural population from different standard chemical elements. It is multi-regression equation show in number of diseases registered in the region, and concentration of total water mineralization, calcium, chlorine, hydrocarbonates, potassium, magnesium, and sodium, and SO4. And for us, very unusual. Determination coefficient is like 0.38. It is very high level, because this show 30% of the illness of the rural population depend from quality of water, but not quality with water pollution, quality water with hydrochemical concentration of chemical elements. And it is true, and for people need some interval between minimum and maximal chemical elements. It's increase concentration, it will increase illness and disease. But low concentration of the chemical elements, it's risk too. And the result can be used to predict the risk of disease from the concentration of substances in the water of water course in the Tashkent region with the expansion condition of 0.67%. And this method can be used for other territories. And Ministry of Health and experts can estimate the risk of increase or morbidity of population when changes concentration on different chemical elements. It's depend from changes field agriculture. For example, sometimes many years on the field used for cotton, but now these fields used for gardens. It is different. It is changes irrigation regime and changes of concentration different chemical elements. This situation can increase of the increase this morbidity for rural population. Thank you very much. I keep 1 minute. Thank you. And I would like to thanks to organizer for invite for this this presentation to this community. We must be think about not air pollution, not only for air pollution and water pollution. We can think about concentration any chemical elements for risk assessments to the rural population health. Thank you.
Perfect. Thank you very much for your presentation, Sergey. And maybe a quick question to highlight again this link between science and policy. What are the solutions or actions, policy actions that can be taken to solve this and to lower this risk of morbidity that you highlighted? Particular, what can the public authorities take as an action to improve this situation?
Thank you. This result use expert in the Ministry of Health, but it is very difficult to show scientific result to the people who is Ministry of Deputy of Ministry. Expert understand it, medical expert understand this, but it is distributed for medical expert and medical career and medical institute, and they use these methods for estimation of risk assessment in the health for rural population for next region. The Tashkent region, it is only one from 12 part of the region in Uzbekistan, and we will use our result in the other regions. Thank you.
Thank you very much for this additional explanation. Well, we have now another question that came, but maybe we can. Yeah, please.
Now, we have another question. So, do you want us to take it now or at the end?
Maybe we keep it for the Q&A session at the end. If that's fine.
Yeah, thank you.
So now I will give the floor to Imad Antoine Ibrahim from the College of Law of Qatar University on another topic, which is looking at the transboundary water context. So please, the floor is yours.
Hi, thank you. We're discussing the legal implication of the use of big data in the transboundary water context. So the first question we ask here, what is big data? Big data is a certain amount of data that we are currently gathering all over the world that is extremely high in terms of volume. It's coming very fast every day. and it's very variable. This data cannot be processed by a normal human being because of that, which is why it was called big data. So it's characterized by 4 V's. They call it volume, velocity, variety, and veracity. There are other things that are characteristics to that. To process this data, we have something called big data analytics, which is a sort of a computer program or a machine learning program that is being developed to try to process this data. So we use big data analytics to process the big data. In the context, so how does that function in the context of water resources? You have satellites collecting water data, the ground-based monitoring, networks, Internet of Things, even social media for like citizens trying to collect certain data concerning, let's say, pollution of rivers or something like that. So all these data are important for the management of water resources, whether it's transboundary or not. What does big data analytics do is that they take all these data together, they process them extremely fast in a way that gets us a certain value that is needed to try to manage the water. So that's more or less fast, the idea. So how can it improve water management? So you capture it, so it's being captured, you store it, and then you process it. Once you process it, you get the new information that is up to date, that is constantly changing. This information can be used to try to figure out the best way to provide information to the parties so that they can process that, so that they can manage the water resources. We're talking here in the boundary context. So, but let's say you want to use this new technology or big data analytics to try to process the information or try to process existing data. There are problems at the transboundary. We're talking about transboundary basin here. The first problem, we don't have enough information. Even though states are collecting information, it's not sufficient. And more or less, let's say you're using a new information, a state may see that the use of this new information may put that state in a certain situation that is less favorable, meaning they need to reduce water sharing for this state, for instance. That's not good. And not to mention that it's a new technology. So we have lack of technical expertise, financial situations, and even know-how, especially in developing countries. So there are, especially because we have a lot of huge costs associated with that. Where, for instance, this kind of technology is being deployed between South Africa and Botswana on the Ramatso aquifer there, and by IBM, Google, and other entities, and they're like making investments in millions of dollars. So it's a lot of money, huge financial costs, and huge technical know-how. So what are the scenarios? Let's say you have a transboundary basin and that is divided between 2 or 3 states or more. So what could possibly happen? Well, all nations may decide to use it. Some may decide to use it. One country may decide to use it, or none of the parties say, we don't want to use these technologies. But all of these scenarios are possible on the transboundary basin, depending on each state's interests and needs. So, but what is the likely scenario? We have something called the prisoner dilemma. So the idea was you have 2 criminals arrested for the same problem, and then they are put into different rooms. So they are being investigated. If nobody confesses, both of them go to prison for 1 year. If both of them confess, they go for the if nobody confesses, they both go to prison for 1 year. If both confesses, they go to the prison for only 3 years. If one confesses, the second one gets a higher amount of years. So these are the scenarios. The most likely scenario that happens in this case is that nobody confesses, so both of them goes to prison for 1 year. This is something called Nash Equilibrium. It's when you have different scenarios or options, Nash Equilibrium is the most likely scenario to happen. So this is the prisoner dilemma. So if we try to apply this to the transboundary basin, what does that mean? So we had 4 options for the transboundary basin. One is that all states use it. The second one, none. Third, some of them. And the fourth, only 1 state. What is the Nash Equilibrium in this case, or what is the most likely scenario, is that all states will decide to use it, whether they like it or not. And there are reasons for that. One is to avoid losing advantage, meaning if I, as a state, I am processing information through new technologies, this means I get new information that puts me in a better position than another state. So it's better for my interest to also process the data through the new technology to at least have the same information. And once you have a new information, that will improve your position in terms of negotiating and implementing water agreements. And that also helps trying to, if you have a certain claim, you could use this argument scientifically to support that claim you're making. So this is what I would call the Nash equilibrium, is that in more likelihood, all the states will decide to use the big data. But let's try to put this in a context of water law, international water law, and water agreements. Currently, the water agreements being established around between states are vague in terms of data information. You have general provisions concerning data information, but that's not sufficient. These treaties are very complicated, like they're not easy to amend. Very few of them are being amended. And actually very few states are ratifying them. And even if they are being ratified, states usually try to interpret the provisions in a certain way that favors their own needs and interests. So it's complicated to apply them. So what are the possible solutions in this case? Well, first question we need to ask ourselves, what kind of treaties we have? Is it a framework convention? Do we even have a treaty in the first place or not? So if you don't have a treaty, then the rationale here is to first, when you establish a new treaty on the basin, to include a certain provision concerning these emerging technologies like big data analytics. Now, if you have a treaty, it's most likely a framework convention on the basis of which new agreements or new follow-ups can be adopted. So if the treaty is a framework convention, the parties can adopt a follow-up agreement, a protocol, a memorandum of understanding, trying to address specifically the use of big data analytics for the management of water resources. And if it's a new treaty, we simply add a new provision. So it will depend on each party, on the context of each basin, and what is feasible. That's assuming that all the parties are receptive to that idea and to use emerging technologies, which may not be the case, given the difference in the technical capacity, financial situation, capabilities of each country. Not to mention other characteristics like culture, needs, and interests. So to do that, we need to also, while including a provision, making sure that any treaty in the future or currently is flexible enough to take into consideration the emerging technologies. Like big data analytics is one of the technologies. One could mention also artificial intelligence, blockchain, and all these kind of emerging technologies, which will impact directly or indirectly water management at the transboundary level. So not only we need a provision concerning the use of these technologies, we need a provision within each treaty providing flexibility on the basis of which parties can amend the treaty when there is a need to amend it, because a treaty is adopted today, changes might happen in 20 years and 10 years, so there may be a need to amend the treaties, which is why we need also a provision concerning flexibility, allowing the parties to amend the treaty, not only for emerging technologies, but also for other changes such as related to climate change. But here we are focusing on emerging technologies. So what I'm trying to say here in the last few seconds is we have a new technology emerging, technologies. One of them is big data analytics. It's being used already in places like in South Africa and Botswana for certain aquifers. This technology is going to change the way data is being collected and valued, and we need to address it legally. These were some of the suggestions we could use to address it in a legal way. Thank you.
Thank you. Thank you very much for having kept on time and for this very interesting, very different views and components regarding, well, from the prisoner dilemma to this necessity of follow-up of farms. So I think we saw very different aspects. So I think we had the comment in the Q&A. Well, the question is, what are the resources of big data? Well, if I understand what this means, it may be related to, yes, what exactly the specificity of big data, and maybe what is the added value of big data. So the issue, I mean, maybe this expands a little bit the question that was asked in the box, but what is the addition of big data and these new techniques that you listed, in addition to the traditional data, and sometimes it has already very difficult for countries to share data, basic data, and how do you think this new technology and big data can improve this data sharing? Do they have any advantage as compared to the classic data sharing mechanism, or basically we have still in the same situation with the same way of promoting data sharing, and now that we have more possibilities because we have more techniques and more ways of analyzing this data. But so yes, the question is, are we more or less still in the same debates as we have in the past with classic data, or the fact that we have now big data, this has we can bring other perspectives that can help countries to cooperate better?
It's hard to address all the technical aspects in 10 minutes, so I'm going to try to simplify things as fast as possible. Big data is not the technology that is being used. The technology that is being used is called big data analytics. We are in an age where de facto we have big data. Big data is the fact that you have a certain amount of data that is extremely big, that is coming fast, that is very variable, that is coming every day. For instance, Facebook every day captures, collects, and stores something about 3 trillion megabytes or something of data. No human, that's only Facebook. No human being can process this data. This is why it's called big data, not to only signify that it's big, but to include all the other characteristics inside it. So we are de facto in the age of big data. That's like, we're going to change that because it's there. Big data analytics is certain program or machine learning being developed because of artificial intelligence by programmers, where you can store all this data inside that machine learning and process it. Let the machine or the algorithms process this data with the end goal of getting a certain result that may be useful for water management. Examples of sources of that, which can reduce certain need for information exchange between states, is satellites. Satellites are not owned by states. They're there. You could, by a company or even a company, can ask to collect data from there and then process the data. And that data can be then shared with states. So that data is not actually by the states, but it can be provided for the states. So that may reduce data information sharing. But that's one source of data or big data that can be collected. You've got the groundwater, like in the case of groundwater monitoring stations as well. And so it also depends on each state. And again, I will refer to what's happening right now between Botswana and South Africa on the Ramotso Aquifer, where you've got IBM and Google doing that for the last 3 years. But we still, I mean, there are too many, I mean, it's very technical to try to reply to all of this in now. So, but if there's something I can refer to the paper I wrote on that, and there's a book coming out on the same topic as well, taking the Ramotso Aquifer as a case study, but it's very technical, but that's how I can provide certain response very fast. But yes, it's very complicated.
Thank you very much for this additional insight, and I think yes, for our audience, it was very also useful. We have other questions that came, in particular from Chandana Witashanashi, who has a very similar question to, I think, from you have already answered part of it, and we have another question that came now, but we will take it for the Q&A session. And now I would like to give the floor to our last panelist, Florence Tanui from University of Nairobi in Kenya, and again on the topic of groundwater. Please, Florence, floor is yours.
Thank you very much. My presentation is entitled Comprehensive Risk-Based Groundwater Research Provides Evidence for Informed or Water Policy and Management in ASALs. And so this research tries to demonstrate some of ways to simplify research outputs for the use by local stakeholders and policymakers. So like most parts of the sub-Saharan Africa, Turkana County is classified as an arid environment, and Lodwar Town, which is its administrative, which is the same, Lodwar Town is the administrative town for the Turkana County and depends largely on groundwater resources for its water supply. It is located on the downstream section of the Turkwel River watershed, which means mainly that it is vulnerable to all the upstream activities occurring within the basin. And so the groundwater here is actually abstracted with a lot of uncertainties. That means there is no information known about the water quality, hydrogeological characteristics, and also issues to do with aquifer processes that actually affects the water quality and its availability. So this slide demonstrates the cross-cutting issues on groundwater use risks. So the main uses are domestic uses, irrigation, upstream, livestock use, because it is a nice upstream environment with limited surface water resources. There is also oil development in the region, which also uses groundwater for the production purposes, and of course the infrastructure development. And the groundwater is vulnerable to two main risks. These are the climate-induced risks and the human activities, pollution caused by human activities. This kind of captures a lot of unknown issues about the aquifer use in terms of future water availability and the quality of that particular groundwater available. And so we used several methodologies to give evidence to these researches. And so we use detailed geological mapping to understand the geology of the area. We also did seasonal water quality monitoring between 2018 and 2019. And we did groundwater isotopes and surface water and that of rainfall to be able to see the behaviors of the aquifer. And so there are four main geological units. These are mainly the metamorphic rocks or the basement system rocks, sedimentary formations, which mainly I want you to give attention to the yellow formation in the map, which is the Turkana grids. This formation highlights the saline groundwater in the area. And so the potable water is only within the alluvial deposits and the Holocene sediments along the Turkwel River basin. And the water samples showed a lot of variable chemistry, and we used aquifer depth to try to understand different variation of water quality and different processes. So the first chart shows sodium and chloride relationship, showing increasing concentrations as you move away from the Turkwel River as expected. And so we had very low salinity levels within the shallow alluvial aquifer. And then at the intermediate depth, the salinity kind of increases a bit. And then into the Turkana grids, we had very saline groundwater. And the groundwater within the alluvial were calcium bicarbonate, which was showing similar relationship with the water type of the Turkwel River itself. And so the Turkana grid shallow aquifer, which is the one on the yellow formation in the previous map, had sodium chloride water type, indicating that it is highly mineralized water. And we used hierarchical cluster analysis to try to classify various water samples in different categories. And it showed us that the boreholes that we didn't have depth information, because there is a lot of missing records of the depth or of the wells or bore testing records that were done when the boreholes were drilled. And we were able to place those unknown depth samples within the categories of the shallow alluvial aquifer, intermediate aquifer, and also those highly mineralized in the Turkana grids. And to understand the water quality, we evaluated both natural and anthropogenic concerns in the aquifer. So in the shallow alluvial implies to the aquifer system, which has depth less than 30. There is issues to do with manganese and iron during the wet season. In the intermediate aquifer and deep aquifer, sodium seems to increase a bit during the wet season as well. And in the Turkana grids, the EC levels were exceeding 5,000 microsiemens per centimeter in the wet and in the dry season. And of course, nitrates tend to increase during the wet season in all the aquifer systems, indicating potential pollution effects happening. And to highlight, this town, Lodwar town, do not have any sewerage facility, and so open defecation is a common practice. leading to pollution to the aquifer if no prevention is taken. And this chart to the right is indicating the water quality indices showing deterioration or unsuitability of the groundwater during the wet season. So the values tend to go a bit higher during the wet season because contaminants are flushed from the subsurface. And the map there indicates areas where nitrates got elevated a bit above the background levels within the town. And isotopes results, I'm not going to show you the plots here, but I'm showing you the maps. Generally, the plots were below the local meteoric water lines, indicating relationship with the modern rainfall. And then we also got to see that enrichment occurred mainly within the Turkwell River basin. And so there were relationships both in chemical characteristics and also in isotopes that the shallow alluvial aquifer is linked to the river basin recharge. And so there is also tritium results that indicated the Turkana grid didn't have detectable levels of tritium, indicating not linked to modern rainfall. It was recharged prior to the pre-bomb regime. And so there are need to do a number of things in the area. That is to regulate the upstream irrigation, also to protect the river riparian zones to maintain the recharge or in the area and to avoid pollution. And so there was also decreasing DXS values as you go from the shallow alluvial aquifer into the intermediate to the Turkana grids, indicating the isotope fractionation in the channel. So we have a bit of decision-making tools. We try to think of ways to communicate our results. And so we delineated parts of the aquifer, which currently part of it is actually underlying the town with no sewerage facility. And we have recommended a number of measures here that there is need to actually carry out city planning to prevent pollution in the aquifer and also to install the sewerage network in the area. And also there is need to use the water quality index to inform development of the groundwater resources. So areas with good groundwater quality needs to be protected and to be developed for the new sources, and areas with very saline groundwater need to be considered for piping. And therefore there is no need to do more development of boreholes and hand pumps in those areas with saline water. And so this is the aquifer conceptual model. Basically, it highlights the relationship between, or to visualize all our results, isotopic, aquifer chemistry, and hydrogeological results. So the recharge is from the river pulse recharge, infiltration, and then we have rainfall infiltration during the wet season, mainly occurring in limited occurrences based on the current observed climate characteristics in the area. And the discharge mechanisms is mainly through evaporation and abstraction for use. And so this model helps to visualize these results. And so our results have had contributions to 3 key documents. These are the county climate change policy, county integrated development plan, and annual development plan, all focusing on to harness and conserve water resources in the county. All these documents are available for review. Thank you very much. This is the end of my presentation.
Thank you very much, Florence, for this very comprehensive and interesting presentation, again showing how the science and result of scientific analysis can be taken by policymaking, as you highlighted in your final slide with all these plans, including climate change plans that are taking some of the results. Just I don't think we have a question from the audience, but a quick question in terms of measures that can be taken to regulate quality, as you highlighted, for instance, regulation of irrigation, establishing buffer zones, and so on. What do you think is the most pressing and would have most impact in terms of improving the situation, considering also cost and acceptance of the measures?
So as mentioned yesterday by some of the presenters, there are regions where we have water, energy, and food nexus being a major concern here. And this is an example of such a region where we have energy demands. There is a dam constructed upstream of our study area, which is using surface water to generate energy. And we also have in the same upstream region, government irrigation projects with no consideration of availability of water downstream. And therefore, if this is not taken care of, basically it will influence the water quality of groundwater, basically because recharge is connected to the surface water. And so what we've done is to first of all recommend monitoring, because there was no monitoring happening for both water quality and also to try to see the seasonal water table variation. So this study lacked that component. We didn't do the measurement of the water table monitoring, but that is now taken as part of the consideration by the county to carry out a monitoring project to be able to understand the water sources. And also sewerage, what they have done now is to fence around the aquifer and to try to prevent further development of houses on top of the aquifer resource. So I think that was a major outcome in quest for further actions, which don't seem further immediate. So monitoring and protecting, fencing around the aquifer were immediate actions.
Perfect. Thank you very much for these additional details, which still allows us to understand better the situation. And thank you again for your presentation. And now I will give the floor to Mr. Stanley Nzama, who joined us. He was playing as the first presentation of today, but so I give you the floor. Stanley, please.
Good. Welcome all to my presentation, focusing on the application of science policy nexus in water resource protection practice in South Africa. To begin with, I would like to acknowledge the South African Department of Water and Sanitation and the University of the Western Cape for their academic and financial support provided towards my studies. It is argued that water resource protection and management is vital towards adequate availability of good quality water for socio-economic development and environmental sustainability. However, such practice requires use of scientific knowledge in the development and implementation of rational and evidence-based policies. Therefore, understanding of science policy integration, where physical basis of natural science is combined with policy practice in managing real-life challenges, becomes critical in translating scientific knowledge into effective, sustainable policies. This presentation provides a practical case study of how science policy integration can directly impact water resource protection practice in the local, regional, and the national level in the context of South Africa. In terms of the background, extreme drought conditions, flooding, urbanization, uncontrolled recreational activities, extreme industrialization, and water quality deterioration are some of the most water resource challenges of the 21st century, which together pose a threat to water availability and food security. Such challenges require policy-relevant interventions as well as evidence-based solutions from science, thus calling for engagement between scientists and policymakers. However, it has been argued that scientific knowledge is often not effectively communicated to decision makers. And in some instances, scientific results are complex and difficult to understand. Therefore, the question is how scientists and policymakers engage each other at science policy interfaces and in addressing social challenges linked to water resource quality and availability. However, in our study, we went further and we wanted to establish and understand how South Africa translates or apply the concept of science policy nexus in water resource protection practices. So our study argued that science policy interface must be practical, reflective, and must consider the nexus approach where scientific results are translated into relatively usable formats. Our study that we conducted followed a descriptive case study design and used qualitative methodology and relied heavily on secondary data which was sourced from peer-reviewed literature, online public available website, and from the government web reports. 3 objectives were formulated to achieve the main aim of the study. The first objective looked at identifying theoretical models of science policy nexus in practice. The second objective focused on studying existing South African policies directed towards water resource protection, while the third objective was achieved by demonstrating how the concept of science policy nexus is practically applied in the South African context. Literature review and document surveys were used as methods for data collection, while analysis and case study analysis, actually content analysis and case study analysis, were applied to analyze collected data. The outcomes of the first study objective indicated that science policy integration, policy science integration, and mixed integration are the 3 theoretical models of science policy interface that exist in practice. Furthermore, the study found that each of the theoretical models guides the outcomes of the engagement between scientists and policymakers. And the findings, and actually such findings, are comparable to earlier findings reported in studies of similar investigations. Results from the analysis for the second objective indicated that policies for water resource protection do exist in South Africa, and such policies are implemented using strategies of resource-directed measures which are scientific in nature. Studies of resource-directed measures allow the state or the government department to classify water resources according to their state of deterioration or change from a pre-developmental state. Water requirements for basic human needs and environmental sustainability are estimated in a catchment, and the numerical limits and narrative statements known as resource quality objectives are determined as conditions for water resource protection and management in a catchment. It is important to note that the resource-directed measures are undertaken following a prescribed procedure. And in this case, our procedure was prescribed or was promulgated in the year 2010. Now, in terms of a third objective, the analysis indicated that difficult and complex results emanating from scientific studies of resource-directed measures are translated into understandable and readable formats by policymakers. This is shown in the figure located in the top left and the top right of the presentation slide. Now, the results are further gazetted or legalized for public acceptance, and they form part of the policy implementation tools. Therefore, the theoretical model of science policy nexus at play in such practice is mixed integration between science and policy. This is shown in the figure located at the bottom of the presentation slide. In conclusion, we reflect on the research question I posed earlier, which is how scientists and policymakers engage each other in science policy interface, and how South Africa translates transcript of legislation into practice using science and vice versa. Now, to answer those questions, I highlighted that there are 3 types of science policy nexus that are used in practice. Number 1 is science policy integration, policy science integration, and the mixed integration. And also it is evident that South Africa is in the right direction in terms of applying the concept of science policy nexus in a way the country is able to use the mixed integration model of the nexus in water resource protection practice, readily available for policy implementation. Now, in terms of the limitation associated with the study, it stated that quantitative factors for impact and adaptation of the nexus was not assessed. And further research is advisable on assessing application of the nexus in data scarce catchments. In terms of the recommendations, the analytical approach developed and tested in this study is recommended for extrapolation in catchments of other settings where challenges of science policy integration remains a problem. Now, we believe that if such approach can be operationalized successfully, improvement in the achievement of SDGs linked to health, water, and food security will be realized. I thank you all.
Thank you very much, Stanley, for this very interesting presentation that is somehow providing some framework also for and perspective for some of the questions and the issues that have been discussed here in the previous presentation. At the end, you were planned as a first presentation, but at the end it was also good that you was last, so that this gives also this insight on the broader framework, particularly on how communicate scientific results to policy audience and decision making. I don't think we have no question in the question and Q&A box. So maybe I will take the opportunity of the last 6 minutes that we have for this session to give the floor to Paddy, so that she can give some insight, maybe some general reflection on the session, which has turned to be proven to be very insightful for the topic of this theme 5 on the link between science, education, capacity building. We will more tomorrow, of course, but and so Paddy, please, if you want to have some words or have some additional questions that you collected during the session to some of our panelists. Thanks.
Thank you very much, Aurelian. And I would say thank you so much to all the panelists. It's been very enlightening and to see the experiences from different countries. I have a few questions. What I'll do is to just throw them out there, and then maybe the panelists can respond very briefly if possible. If I can start with the last presentation, I found it very interesting that South Africa has made so much progress in terms of the science policy nexus. And so my question is, what has been the enabling factor for this? And I think that ties into the other presentations as well, because for Diana Mudimbo, I was going to ask, what have been the main challenges in terms of the methodological aspects of working with people from different fields, because that could not have been easy. So what were the main challenges of different scientists working together? And then for Disha Gupta, did you also consider the equity aspects of things? You know, because if you think about the policy implications of raising prices or not raising prices, and then the farmers' access to powerful agriculture, do you think that looking at the equity side, the inclusion would affect the policy recommendations that you're proposing or not? So those are the main questions I have, and I hope that we can speak to this very briefly. Thank you.
If I can respond. With the issues of working in a interdisciplinary or multi-interdisciplinary team, it's a challenge because when we work in our groups, we have certain terms that we use for a start, and we assume that everybody else understands. They're quite technical, and there's certain ways that we conduct our research. In particular, when we look at hydrogeology, for example, where others would kind of loosely use the term of groundwater recharge, we're a bit more particular about what does groundwater recharge mean, what have we used, what techniques have we used, and how robust are those assessments and those measurements. So being able to initially get to the same understanding of what terms we're using in terms of scientific terms and what it means for the different disciplines made a huge difference. And there was a bit of a learning curve for all of us first, and then we could understand what we were talking about. What does CA mean? What does it mean in terms of the impact of the size of the plots? Can we actually measure groundwater impact on such small plots? You know, why is it not so easy? And what methods can we implement? So multidisciplinary has its issues. We have to be open initially to learning, and then we can move off from there in terms of being able to make a difference.
Thanks for that.
May I get to the next?
It's okay. So if I can give a feedback on our approach to getting our research to be taken into policy. First of all, the research was funded by REACH project by FCDO through the REACH project. And so what we did, the project aims at improving water security for the poor. That means we had different cross-cutting issues that we were investigating, not just groundwater. But what I've reported is the groundwater part. So we were doing social economic studies or based on household surveys also to investigate characteristics and water demands of these populations, and also infrastructure, which was an engineering component to develop climate resilient infrastructure for arid lands to make the water available at residents. And so all these issues are mainly focused on where is the groundwater itself before you distribute to the most vulnerable groups. And so what Rich did was to have an office in our study area. This office, we have persons employed by the project to be there and to be able to avail information where needed to the various stakeholders. And so at every stage of our research, from reconnaissance, we were briefing the county governments, because water is a default function in Kenya. And so the issues of groundwater management use and can be specific to a certain county based on the dynamics which are there on the ground. And so when we are also involved very much in what is going on at the county levels in the Ministry of Environment, water resources, to be able to address the challenges that they have. And so we realize one of the key things that happen there is we have donors coming to provide wells for the communities. But then when a borehole is found to be dried, it is left and the funds is not used now, or it goes to a loss because a borehole is an expensive venture, for example. And so what we needed to do is to delineate areas for good groundwater quality and empowering the county or the water resources office with our information to make them functional, because what they lack is basically information, and the funds they have is not enough for them to do such comprehensive work within a short time. And so involving them and breaking down information, like water quality index is known and used mainly by almost everyone. And so we kind of use that tool to give them, anybody can see, when I drill a borehole here, of course, it is based on whether the groundwater is very saline and it has too much sulfate, chloride, all these components of groundwater quality, then they will not be able to use to dig a well there. And so by doing this, the community feel involved. All the stakeholders are also feeling like they are empowered because they have information. And so request for information is a very key component of the REACH project. So if anybody requests for information, we document that, because we kind of track feedback on how the information was useful. And so this is a very good approach because we've seen quite a number of changes and making the office to be like dependent. Someone has to get there every day to request for something. And so I think being available also as researchers is important. It's not like you go to a certain study area somewhere. It may not be possible, but it seemed practical for our case.
Thank you very much for that.
And thank you very much again to all our presenters. I'm afraid that for the sake of time, we have and so that the next session starts on time, we have to close our session now. This is unfortunate because, of course, as we could hear from Pedi, also the other question that she had, this is very passionate subject of this interaction between science and policy. And we hope that some of the will be answered individually on written and shared with you on the conference website as a follow-up of the conference, together with a video recording of this session. Of course, I invite you to attend tomorrow, especially the second part of this theme 5, and we will have Pedi again as a co-moderator, and the main moderator is Lesha Wittmer. So I invite you to connect again tomorrow for this session, and in case you want to hear more about this interaction between science and policy. Thank you very much to all, and have a good day or good evening.
Thank you.
Thank you.